into numerical features. So that's what you like to do. So here, like I would be a word. There's maybe 1 million possible words in English, or I don't know, maybe only like 10 or 20,000 of them are used frequently or so. I don't know. And then for every word, we want to have a real number representation or many of those. So here we're looking for like k features for that word. So so that's the goal, and there's of course several ways to do it. So how to translate a word into features. So and I guess so here, yeah, what k? How many features to get a reasonable representation? And I would say the very easiest way to do it probably is to use this kind of Onehot encoding, which just means to set the vector of the ith word. So sorry, so wi is the word, and I map it to a vector, which is also called wi. Just a 1 here where the word appears, and it's 0 everywhere else. So this is maybe the easiest thing you can do, and so this is the position of I, right? And I can be which word it is from whatever is your vocabulary size. Let's say maybe 20,000 is a reasonable vocabulary size. So that's k. So and this is this yeah, standard Onehot encoding, and when you do it this way, what's this is also known as the bag of words representation. And that's because you could also do this when you have more than a word, like a small sentence, 3, 4 words together. Then all the words that appear, you put 1s, right? And the ones who don't appear, you put 0. And why is this called bag of words? It's because the order of words doesn't matter at all, right? So if you have these 2, 3 words, then you will have some 2 or 3 non-zero positions, but everything else is 0. And we forgot about the ordering of words. And if you just do it for 1 word, then here is the mapping. And of course, this is a vector in k dimensions, and k is really big. So this is already brings us a bit to the discussion of this kind of feature representation. So one quite obvious downside is that it's very expensive to deal with such vectors because they are so large. I mean, if you deal with individual words, it's fine. They're sparse, the vectors, right? But as soon as you start to learn a classifier on these features, then the classifier would be a dense vector, taking such vectors as input as data vectors. And then this is going to be problematic to have so many features. So, okay. So yeah, finding good features. That's the topic here. And then also, yeah, what do we really want? So, okay, we said it's problematic to have too many features, but also, okay, if I have fewer features, then what are good features? So, because here you can also see that it doesn't capture much, it doesn't capture anything smart, right? Every word has going to be a completely different vector here. So, for example, a word in singular and then the same word in the plural form, they will have completely different feature vectors here. There's no way that these 2 feature vectors tell you anything that these words are related. So that's what it's a desirable thing that we would like to have to also capture the meaning of the word a bit, to get features which are kind of reasonable, right? Which capture what is actually the hidden, the true meaning of the word, or the useful information in that word. So what would be much better is to get something where similar words have similar feature vectors. That would be the goal, right? So that would be much nicer. So that is also that's always when you do representation learning, then that's what you what you would kind of like to have. You would like to get features which reflect the true meaning of your input, right? For an image, also the pixels are not that, right? So for images, the best methods are to take the image and let it be processed by a neural network, and then maybe after a few layers you get the representation. So that's the activations that this image gives to the network, and these are much better features. So because those at the very deep layer of a neural network, then maybe the last layer, it's going to be a very good classifier on, for example, the ImageNet data, which can classify thousands of different types of images, right? So it understands the semantic of that image. So the features at the end, they understand the semantics, and the features at the beginning of a network at the input, they don't. So, and this is a similar thing here, right? So yeah, maybe those vectors are good as a raw input, but they're maybe not the best features you can have for words to do some smarter analysis later to capture their meaning. So this is only a starting point, and this is called the bag of words representation. So the obvious question now is, can we get better features than this? So, and of course you can use neural networks, but before we do that, we actually see a simpler and much kind of more elegant way to learn feature vectors, and it's very similar to what we have seen on Tuesday. So the goal now is to learn a feature vector for each word, a word vector. So this what we're going to discuss now is also called word2vec and some variants of this type of methods. So to learn these vectors, we have very nice unsupervised data available. So what we're going to use is a matrix here, which looks very similar to what you have seen on Tuesday. And this matrix is super trivial. It's just counting how many times does each word appear with each other word. So here is the row for word I, and what that's written here, 1, means that with this word J, which would represent the column, those two words appear together in the text maybe once or twice if you ask about this other word. So these are the counts. How many times did the word I co-occur, so occur together with word J? And yeah, what text am I talking about? So this method, you can train this on any text. So all the text in the world, usually, the more the better. You would just throw entire Wikipedia and all the text you can get. You throw that together, and then you compute this co-occurrence matrix, which just counts like these words occur together, and occur together is usually like just next to each other, right? Or in a small window. And yeah, that's it. So okay, by the way, how would you compute this matrix? Because so this is actually a really gigantic matrix, because again, this 100,000 of words is our vocabulary size, and it's that vocabulary size squared. So which is a large, very large number. Any ideas from your side? How would you efficiently compute this matrix on a huge text corpus which you cannot load into RAM? What do you think? So, yes. Yes, you're right. You're saying the result is a sparse matrix. That's true. But computationally, it's still challenging because even the input is super big, and you're right. The result is sparse. Yeah. But how could we parallelize the computation of this, and to make sure we don't need to store all the text in the main memory, or how would you parallelize computing this? So yeah.
We just make a bunch of them on separate
Yes, so you're saying you would separate the data into several parts. That's true. So yeah, you do the English Wikipedia, I do the French Wikipedia, whatever, and then compute this matrix individually and then add it together. That's correct. That's exactly how you parallelize this. And what is this paradigm called? You maybe have seen this before. So yeah, MapReduce, exactly. So MapReduce would be the nicest way to compute this gigantic matrix on a huge corpus. Yeah. So yes. Okay, should the matrix be symmetric? Yes, the way I presented it, yes. But there's a small technicality that you can have more rows or columns. So usually it's symmetric, yes. But if you want, you could also, so here are the words you care about, and then the ones in the column, those are called the context. So the ones that you care about how you occur with another word. So, and theoretically, you could have a different vocabulary for the context, so you could have a bit different number of columns than rows, but in reality, yes. So t equal n in reality. So, but just in case, if you want to say that, okay, this is a different set of words I want to compare feature vectors on, and there's a different set which I take as my context, that's also something that you can do. So here the rows are the words, right? We compute a word vector for each, and then the columns here are the context. They are also words, right? So WJ, but they could come from a different vocabulary. But yeah, you're right. In reality, this is usually the same. And then yes, it's probably symmetric. You can define what you mean by co-occur. Actually, what we usually do is to appear together in the same window, right? Just next to each other. Maybe that's what it means to occur together. Or actually, in WordDirect, so they use like a window of size 5. So if 5 words apart, so that means that the 2 words still appear a bit together in the same sentence or same context. So maybe they're a bit related. So okay, this is just very naive computation of frequencies. We didn't gain any additional information doing that, right? This is just the most basic statistics of a text corpus. It's basically just the text itself, and you counted it. So not much has happened yet. But yes, what's interesting also is that this is a sparse matrix, as you mentioned. So let's keep that in mind as well. And then if you look at the figure, so now the whole story here, it reminds us a bit of the recommender system example that we saw on Tuesday, right? So it looks very similar, the story. So the data looks similar. So there we had star ratings, 1 to 5 stars for people, items and people together. Here we have these counts for 2 words together. So can we maybe use a similar approach as in a recommender system? And the answer, of course, is yes. We can also try to make a matrix factorization of this, and that's basically then. So now something interesting happens right now. If we do this, then something will be learned. So and so now this is size k, this is size k, and sorry, that's Z transpose. As usual, I will just factorize this gigantic matrix into 2 smaller matrices. This was d times n, right? And so what's the point? Is exactly the same as in a recommender system. You just ask that, okay, I'll do this. Hopefully, if I do it at the vector of word I times the vector of word j. So here is I, here is j. They get multiplied. and hopefully the score you get. So when you take the inner product of these two, so that's the entry ij, right? That's this entry we have here. Hopefully that entry will be similar to the score from this matrix factorization. So now we have a learning problem. So this is given and this is learned. W and Z are learned. So we will optimize them. So we will throw exactly the same machinery as we had in the recommender system. We can apply it here. And then every row of your W matrix will be your feature vector. So now you learned feature vectors and you learned such a vector for each word. So these are the rows of W are the word vectors. So that we learned here. So, and yes, so that's basically, that's the idea. So for every word now you have learned a word vector, and now this of course you can do for any much more reasonable, much smaller k, right? So you can choose k to be whatever 10 or 50 is maybe a reasonable number. So you learn 50 features, even if your vocabulary is 100,000, and hopefully these features here, these 50 features will be very good to also carry the semantic of each word. Because if this is true, that the inner product of the two explains the score, then it means that those features here, they kind of reflect the meaning of the two words, right? They can explain that, yes, these two words often occur together, or no, they don't occur together much. So if this works. So super simple approach, and it's kind of nice because it's really unsupervised, right? This is now, I think we agree that this is like fully unsupervised. There's no human labeling has been necessary. Text is just there. So, and from that we can learn features. So that's why it's representation learning. So this is learning word vectors. So this is really the idea behind WordDirect and GloVe. So maybe you've heard of WordDirect. So I'll come back to it in a second. And the other one is called GloVe, which comes from a global vector learning something. So both these methods are very similar. So the one we talked about now, which takes this matrix and factorizing it, that's the one called GloVe, which is from 2014, I think. And then WordDirect was a bit earlier, 2013, but it's a little bit different. So we will come back to that one. And they have really had a huge impact on anything which has to do with text, right? So to kind of, it's kind of a big step, right? From these naive vectors which we had in NLP traditionally, the few decades before these word embedding methods came up. So here we had like a vector in 100,000 dimension, very sparse, not carrying any semantics. Now we have a vector in just 50 dimensions. And mathematically, it's super simple, right? It's again just a matrix factorization. Now every word has a vector of 50 features, and we can do machine learning with those, using those as a feature. So that's GloVe. And the cool thing is, it's again a very straightforward application of this matrix factorization, right? That we always we encounter now already a few times. So here is the data, X is the co-occurrence. Is this given co-occurrence matrix, and you factorize it into the two factors. Okay, maybe now it's time to be a little bit more precise on what exactly is the loss function in this case. So it really looks the same as we had in Netflix. So this part is really the same, right? So X is kind of this counts, I'll get to that. And then the factorization, as we said, and you just put a squared loss. So this was the same as in the recommender system which we discussed on Tuesday for these Netflix star ratings. Then there is a very small modification here. It's this F, which is in front. This is a very small, I think, sorry, not, it's written in small font because it's it's just a weighting factor. So I'll come back to that. So there is this, a scalar here which we use to give a bit more weight to some kind of important co-occurrences or not so important ones. And then omega as well is just the entries which are observed, right? Because of course there is, well, okay, that's not obvious, but the point is we don't do anything for the entries which are not observed together. So those will not be included in the loss. So so omega again is the set of the non-zeros of these counts, right? So yeah, we treat it as a sparse matrix, as you said. I would say mainly for computational reasons. So it's more efficient to ignore it's more efficient to ignore the zeros, right? This is actually a bit different than in the recommender system case, because here the fact that the stuff here is zero, it means something, right? It's actually interesting that these two words never occur together. It's actually useful information, so you could try to use it. But in the Netflix case, this was different because here this was missing because there was really no information there. We have never observed movie I with user J, therefore it was a missing field, right? But here it means that the words do not appear together. Still, I use the same approach. I ignore it. I only use the information from the non-zero co-occurrence counts. So you could play if you also want to use all the entries. You could do that. What you can also do is you could just take this matrix and perform a PCA on this matrix, or singular value decomposition. There would be another very easy way to get a factorization. Actually, that also works quite well. But it turns out that the method here, which ignores the zeros here, even performs a bit better. It seems to give vectors which are a little bit more meaningful. I don't think there is a theoretical understanding for this. Because it's also a bit hard to evaluate these vectors. We cannot really prove that they are good in my sense. We can just empirically evaluate them. Are they good features for other NLP tasks, right? And yeah, you can also just do the SVD of rank K, then you also get features. Usually those from this or from WordDirect perform a bit better, but you can maybe play around with that if you want. So this week we also have a nice lab where we give you such a matrix and you can run the factorization. You can use the same code as you had for the Netflix case, basically. So yes, so that's GLOF. The objective function is identical to the Netflix recommender case, except the small weighting. And also the other thing is what is X. So this is actually the counts together, but I need to be honest with you that this is actually the logarithm of the counts. So the log of the number of co-occurrence. Because some words are just extremely frequent together, like the word "there" together with, I don't know, they have like a huge frequency. In text, you always have this kind of long tail phenomena that some things are extremely frequent and some things are extremely rare. So it turns out it's better to use a log scale input here. So the X data which correspond to these ratings, these are, yeah, the log of the co-occurrences. Okay, so we take those. So those are actually all logs. And then we factorize it, log 3 and so on. And then we compute the factorization, and then we have our word vectors. So is there any question on this? I have a very small addition on what these weights actually are. So again, this is not hard science, but a bit more empirical to how to what weights could you use. So what they found nice is what they found to work well is to use weights which grow with the frequency of the word. So here is the frequency of a co-occurrence. And I mean, we already have it kind of in the log, right? The log already means that this thing grows kind of slowly with the original count, right? So that's already in the X. But what they did here is that they added this auto weighting as well, which also has a bit the same spirit that when they're very rare, they should not be counted much. And when they are extremely frequent together, then they should be counted, but also there should be some kind of cutoff that you should not put like too much weight. And this one is outside the square loss. So that's why it's a bit different than just reweighting the X, which of course is also something you could do. So, and what they did for the weight is something like this, so that it grows kind of almost linearly, but this is a bit curved until a cutoff value. So what this means is, it just means that after it has occurred together 1,000 times, or I don't know what the actual value was used, after it's like 1,000 times and you don't care anymore, then you would just set the weight to 1. So it's constant when it's higher than that. And the curviness here is that they chose some kind of exponent here to make this growth a little bit curved, not linear. So alpha here is this kind of growth rate. And this is very, very empirical. It's not that this is a true theoretically justified thing, but this is something that turned out to perform really well for the resulting word vectors you get. But if you want something simple, then you can just ignore these weights. So and just set them to 1. It still works, right? So also, of course, if you just decide to compute the SVD on X instead, then there's nothing like that. There's no weighting, and so this is actually another reason why maybe this method could also perform a bit better, because it has some kind of smarter weighting, which the SVD cannot. The SVD will just go for the big entries and make sure they fit, because it has to explain all the variance in X. But here we are a little bit more fine-grained. We can say that our loss should focus a bit on the words which are together, which appear together a bit more, like in the reasonably often case. So this is not, the idea here is not to be dominated by those things which appear a million times together, but to be a kind of in the interesting regime here. And also the rare co-occurrences, of course, also appear nicely in this loss. But the main contributions, I think, are from like the middle, the ones which are like usually frequent and not super frequent. Okay, so a very small modification to the loss function from the recommender system. So, and this is, if you all put this heuristic together, so and so on, then you have GLOF. And so then you get these vectors. They also offer them pre-trained. You can download them, and this is also for Word2Vec. Usually, when you would like to use such a method, then you don't train this yourself usually, because other people have already done it for you. They have run MapReduce on Wikipedia or web crawl to compute the co-occurrence matrix, and then someone has run stochastic gradient descent to compute W. The Z we don't even care about. This is the embeddings of these context words, so we throw them away after training, but we keep the word vectors in W, of course. These are the representations of the words that we are interested in. So you can basically just download such W matrices sometimes even for several languages and so on. So that's also something we at some point tried to work on to get these word vectors such that they are similar when the word has a similar meaning in different languages. Because this matrix, you could just throw all the languages together, it's fine. Just the web is very multilingual. You just compute all the languages together, you get embeddings of words of all languages, but then maybe you can do some trick to encourage words of the same meaning to have similar vectors in, even when they're from a different language. That would be an addition to the basic method we have seen here, but no worries. We're not going to discuss the multilingual case much. So yes, this was this hack about the weights, and then the usual discussion we always have. So how to choose K? It was a discussion when we had K-means, where it was number of cluster. It was a discussion then on Tuesday when we had the recommender system. There it's a similar thing as now. It's the features, number of features we want. And for text applications, what you find is usually smaller values around 50 or so work quite well, but then there is more advanced word representation since then. For example, from transformer neural network models. One of them is, for example, BERT, where they go up to 700. What's the number here? Not 0. So they have up to 700 as which they use as the dimension or how many features they produce. So it's some power of 2. Okay. Yeah, which one? So well, because you also need to store this whole matrix, which is quite big, when you have 100,000 words times K, and this, of course, is a dense matrix, right? Even if this was a sparse one. So the word vectors are dense, but they are quite short. So K, of course, is much smaller than the vocabulary size. So depending on your storage requirements, maybe if you want to run this on a phone or so, then you might have to choose a bit smaller K to fit memory constraints. But yeah, on computers, you can have several hundreds of K. I would say it's not a problem. So okay. Okay, now why is this cool? So I again mainly just gave you the math and how the algorithm works and input and output and so on. So now we have these word vectors. So why are they useful? Why are they better than what we had before when we just had a bag of words? So some things that you probably have seen of some of these analogies. So who of you has heard of this king and queen example? So some of you. So the idea is that, interestingly, when we now look at these word vectors, we see some interesting correspondences, and we see that similar stuff is grouped in similar places. That's nice. But not only that, we also see that there's interesting relationships. So, for example, yeah. So the words king and queen, they're embedded somewhere. So here are these two vectors, and they seem to have a similar direction than man and woman. So that's kind of interesting. Why is that interesting? Because then you can do this kind of algebra. You can say, yeah, you can say the vector. You start here with man, for example. So the word for man, then you subtract sorry, word for woman plus, sorry, I'm messing this up. So then what you see is that these vectors, man minus woman, is approximately the same as king minus queen. So and this pen is messed up. So if you take it to the other side, you can do this kind of algebra. So man minus woman plus queen. So now this has gone to the other side, and then you see that you are somewhere, and that word happens to be something very close to king. So I mean, okay, what's the point here? The system has no idea what these words mean, but the directions in space are meaningful. So the directions, there is a direction in the space which reflects the difference between, I don't know, regular people and royalties. And there's also another direction for gender and so on. So you can do some kind of algebra and you see that this is reflected in the geometry. So that's kind of nice. Also you can go from a country to its capital. So it's just a vector, right? So, and the idea here is that this vector transforms the country to the capital. So now if you take this vector and attach it to another country, like Russia, you go in the same direction, the direction towards capital, you end up somewhere in space, and you ask what's there, right? So you ended up at a point and you see, okay, there's nothing there, but close to it there is another word which the closest word happened to be Moscow, right? So that's the idea. So there is a direction in space which reflects country to capital. You can do it the other way around. You can take it's always this analogy, right? So Germany is to Berlin like something is to Tokyo, right? And that something happens to be Japan. So that's what you can do in these spaces, that you can ask this. You can do these translations and then ask what's there. So because it's a correspondence to a translation in the other in those concepts also is reflected in the other side. So or yeah, you could ask about airlines and so on. So it's not just doing some naive grammar or something. It's really smart enough to relate these airlines to. Yeah, if you ask Belgium is to Brussels airline, then you attach it to Greece. You really, it's not going to tell you Greece Airlines, but it's really smart enough to give you the correct airline, because those happen to. It's the space. So why is this? So okay, there's a lot of work trying to explain this. I would say there's no hard theory for it, but the idea is that the space is kind of small, right? There's only k dimensions. So to reflect, to explain all the things appearing together, to appear. So here, you need to explain every co-occurrence of words, right? So, and to do that is quite a difficult job. So doing this with just inner product, it really puts those vectors into places such that it makes most sense. So, which then turns out to be nice, that the places where it's put actually become kind of meaningful. Of course, there's also many failure examples, and I mean, this is not how you would really productionize a system to do, for example, question answering, right? But it's still it's encouraging, right? It shows you that the words, the meaning of the words is reflected. So, and there's much more you can do, right? So there is also this kind of information retrieval you can do. If you, of course, it's the similarity, right? So, so even before you do this analysis, the much simpler thing to do is similarities. So there you just ask a query word and WQ, and then you ask what is the word closest to this. So, or So I mean a query vector, right? So any vector you have, then you can ask what is the word closest to it. That's actually what we did here as a small building block for the analogy. But then things like this can be used in web search as well, right? So okay, the user is searching for this word, but maybe we should also offer the user results for similar words, which means the ones which are nearby in this vector embedding space. And I think just this week, Google actually launched a new product which is called like vector search. I don't want to, I haven't tried it, but it's the same idea that yeah, words and also other data modalities are embedded in a space, so that then you can search from that space to ask what items are actually close to the item you're looking for. So I mean, there you even for images, of course, you can ask for similar images and so on. But here, it's nice to do the same thing with word representations as well. So, okay, we have retrieval as applications, information retrieval, and then these analogies are more fun thing to play with. You can also try this out. There's some demos on the internet, and maybe in the lab, if you train the word embeddings, you can also see which words happen to be closest together. It will surely do a great job on like things which are really almost synonyms, or like the plural and singular, they will be embedded very close to the space. And also this example we have here. So for verbs, you will also understand that being a past tense, so swimming and swam is the past tense of swimming. So there will be a direction in space. So first of all, they will be rather close. And second of all, the direction here will be kind of meaningful, that if it's past tense, it's always shifted into one of these particular direction. Past tense. Okay, that's the idea of word representations. And you would also ask how to train this. And there the answer is exactly the same as we had on Tuesday. So there's nothing new here in terms of algorithms. Basically, it's again just a SGD, and the nice why it's so good or preferred is the efficiency per step. Is only order k, right? So we only need to spend k operations to multiply the two green vectors, right? So we sample one entry at random, and we do the inner product, which gives us the prediction. The prediction is 1.5. We compute the loss, so the loss is 0.5, and then we update our W vector, and only the green one will be affected, and only the one which is currently active. Everything only costs k, which is very nice. So yeah, you just do uniform sampling of these entries, and then yeah, later when we talk about Word2Vec, we will see if there's maybe there's even smarter way to do this, to actually stream through the text, to just see the words which are appearing together right now. But that's not what we're doing here, right? Here we already know that, yeah, the word appeared 3 times together. So it's not a streaming algorithm. First, you need to have this matrix, and then you do a stochastic gradient update for every entry of the matrix. And the entry has to be chosen at random usually. Or you could also, yeah, maybe have a permutation for this ordering in practice. Okay, so SGD is the answer, and that's also, see the lab of this week. We have a nice code template for you, very easy to do. And there's also possible to do with alternating least squares, same as in the recommender system, but I would not recommend this, and we don't do it in the lab. So, okay, interesting related questions, if you want to go further, would be to how to parallelize this. And we already talked about how to parallelize the first step to compute the co-occurrence matrix. That's easy with MapReduce. But then there's a bit more to do if you really want to run SGD in parallel. This can also be done. So then the question is, maybe can you partition this matrix into several workers and still have good SGD that, yeah, the worker 1 works on these entries and worker 2 on these. So that is a bit more tricky to, because SGD again would use a random sampling of these elements, which are, this is a sum, the loss function is a sum over the losses over each element. So that's another interesting question. And then also you could regularize a bit, but that's actually rarely used for word vectors. I haven't seen it. And a downside is to need to pre-compute the big X matrix in the beginning. So we know how to do it, right, with MapReduce, but it's still a big matrix. Even if it's sparse, this is a gigantic matrix, and it's not so nice that once we have computed this big matrix, we need to have it in memory to basically run SGD on it, which is not entirely trivial if it becomes like really big. So that's why after the break we will talk about the original Word2Vec, which is almost at the same time as this, which then solves this problem that it does not need to pre-compute this co-occurrence matrix. It's actually a streaming algorithm where, I mean, streaming through the text. So that's for after the break. See you then in 15 minutes. We are back, and we will wrap up on text representation learning. So this was maybe a bit the technical part about GloF, and now I want to switch to the one which is a bit slightly more used in practice, which is the Word2Vec one, which came up at around almost same time, so 2013, and so which is again is very related to what we discussed. So very similar method to find good word representation vectors. So what's the difference between Word2Vec and GloF, what we've seen here, right? So this was GloF, just find the matrix factorization. And now we want to ask a bit about this one. What's the difference here? And the difference is basically mainly that we get rid of this downside of the pre-processing this huge X matrix, which is vocabulary size squared, but then it's kind of a sparse matrix, but this is a big effort. And at least the nice thing is, yeah, why is this big, right? Because we can really use X can reflect all text in the world, right? That's the nice thing. You can really use as much as a text corpus as you can get, because it's unsupervised. So that also means that it really benefits from having as large text as possible. But maybe we cannot store the whole X matrix in memory. So is there an approach to overcome this problem? And then, so what Word2Vec does is basically, it's exactly the same idea, right? So the goal is completely the same, right? We just try to learn word vectors W to reflect our scores, and the way we do this is exactly the same. So we just build the inner products of the word vector with its context vector. So this has a few entries, right? And of course, same for the word vector. So here's the word, and here's the context word. So that's the same as before. These were the two green vectors we had already in GloF. So what is different now? The difference now is that we don't care that this is giving the total count of these two words D and N, right, appearing together. Sorry, we called it I and J last time, but it's the same thing. What do you want to predict, right? So the product of these two guys is a number. So what should this number be? Before it was, our goal was to be the total count of these words together. But now we actually do something a bit simpler. So what we ask is, we just ask to classify yes or no. We just classify that yes, these two words are from a real co-occurrence. So I stream through my text and I see that, yeah, word D and word N, they really are next to each other. So they appear together. So I kind of have a binary classifier to answer. The classifier should answer yes. So so positive score. So, and then, but then, okay, if you do this, then why don't you just always answer yes? And you wouldn't learn much doing that. So when we do this classifier approach, we should also sometimes answer no, and so that we can actually learn from what's the difference between yes for current occurrence or a no. And the difference is that for what could you use for the no examples? So any suggestions? So in which case would you say that, okay, the classifier, so the classifier is just a product of these two, right? So just the inner product. So of course it's some value, maybe it's positive, maybe it's negative. So if it's positive, it means yes. If it's negative, it means no. So which word pairs should the classifier answer no? What do you think? So I mean, we said we want to answer yes if they really appear next to each other when I go through my text, and when could we have no answers? So we want to have a bit of a mixed training set, right? We want to have both kinds of situations, not only yes answers. So for the no answers, you would just put fake pairs which do not appear together really, right? So you just, I mean, maybe you just keep the same D, but you put a fake word N, right, which do not appear together. So then so the ones which are so these are called the negative samples. So here is D and N not this means that they're not next to each other in the text, and then the classifier should answer no. So that's it. And well, how do you get those which are not appearing together? It's actually we do even something even simpler here. We just sample a random word. So I mean, maybe D is given, and N, you just sample any other word, right? The chance is super small that it's actually the one word which usually appears together. So just sample fake words. So take any random pair D and N. So those are the ones which we call the negative samples. So those are the ones which are not appearing together, and those are the real ones which are actually next to each other in the text. So you do this while you stream, while you read through your text. So you have a real co-occurrence, and then here you have a fake pair. So this is a real D and N pair, and then here is a fake one which is not appearing together, and that's it. So yeah, this is maybe, so again the word D is maybe fixed. So that's we are currently seeing this word. We see it truly next to the other word N, and then we do not see it next to this other fake word, which is the negative sample. So maybe I should call this, maybe I will call this N prime, right, to make clear that this is a different one, a fake word, right? So N and D are together, and prime and D are not. So this is the fake word. Okay, so now what we have done here is we basically took a big corpus of text, and we have interpreted this text as training data for classifiers. So which is kind of cool. So yeah, what's the classifier here, right? Every word has its own classifier. So the yellow vector is the classifier. So every word has its word vector, and that same word vector acts as a classifier. So if you take the word vector and you pair it with a one which really appears together, you get a positive score. So because they are close in meaning, so they will also be embedded in a similar place. Therefore, if you're close together in space, then you have a positive inner product. So and then the ones who are not together have a different meaning. So those you say, I want those to have a negative inner product. So the classifier, which again is the yellow word, if you want to say, should have a negative inner product with a fake word. So that word should be embedded far away. So this is our training objective. I want to have a high score for co-occurring. So then score should be high. And then if I have not co-occurring, I want a low score. And you really can use the same kind of scores as for example, in logistic regression or some loss function like this, a classification loss function. Yes.
The embedding for a word has a WD, and for the same word as a context word, are those two embeddings different?
Yeah, your question is every word has here a word embedding, but then the same word might have a different context embedding. That's true. It's a similar situation as we discussed before with love. So yes, if you want, you could make them the same. It doesn't really matter. So actually here, actually they use different ones in Word2Vec, but it doesn't matter much. So the context embeddings, you will throw them away anyway. We don't care about them. We just care, they're just there to train these guys. And that's exactly the same situation as when we did the matrix factorization. So these guys we interested, and those are just for the game of training. So they help us. So context embedding and word embedding, and yeah, both is fine. Okay, so yeah, binary classification. It's kind of a cool interpretation that you can go from text to binary classification. It's also very cool to have a different classifier for every word. But then the thing which is really the best about this is that now this can be trained while just streaming through the text. So you don't need to pre-compute any co-occurrence matrix or anything, nothing. You just read text. You start with the Wikipedia letter A. You see the first article, the first two words are there. And once the first two words are there, then you already have your first step for this. So that's the first example for your classifier, the first training point. And it's to run stochastic gradient descent with this first training point, which is to say that this data point needs to be classified yes. And then the next step is to use the same word with a random sampled one, and there that's your first data point with a no answer. And then you shift in the Wikipedia text to the second pair of words, and you just read through the text and do an SGD update on each of those every time. And that's the Word2Vec algorithm. So yeah, and the crucial thing is really the streaming through the text, the input text, right? So this is your entire input text. So the first word, second and third word, right? So and you immediately start. So you start the first word forms the first pair, right? W, D, W, N. So this is your first pair, and then you just continue. So then you keep reading. Okay, streaming algorithm is very nice. You don't need to memorize any text, just stream through it, and again, it's based on SGD, on this logistic regression loss function. Okay, so this is again an illustration that maybe the important thing is not so much which neural architecture or so you have, but the important thing is to identify the opportunity of what signal to train from, right? So, and the signal to train from here is really smart, right? I think it's a really cool idea to say the fact that two words appear together right now, that the two things appear together, that can already give me a stochastic gradient update. That's a learning signal. These two appearing together is a yes, and these two not appearing together is a no. So I will immediately use this information while I encounter information in the world, right? So this can be used more generally. This can be used for any things appearing together, right? So people also use this for maybe recommender systems on the web, right? So then you have people like you browsing the web, you appear together with this item they want to sell. So that happening is also such a signal, right? So you and this item that you looked at it, that's a positive signal. So you will update your embedding and the item embedding based on this yes answer. And then you will use a negative example of an item you have not looked at to do the SVG update of the negative sample. So then you learn embeddings of people browsing, and you learn embeddings of things, products on sale. This is another example of this. And the whole field of this is, so this idea to use real against fake occurrences to learn is called contrastive learning. So contrastive learning, and it's cool because it's unsupervised. You don't need manual labels, and that's also getting quite a revival at the moment for even for example for images. That can you use tricks like this to use no human labels anymore, or much less human labels, right? So again, the tricky thing is to identify the learning opportunity, not so much which kind of machine learning model you use, but what to learn from. So that's this contrastive learning. There will be much more to say about it. Unfortunately, we don't have so much time. So I think that was mostly it for representation learning on text. But what I also want to do is to tell you a bit more about one other thing, which is in a way also representation learning, but it's a bit more, I don't know, it's just another very natural thing you can do with sequences, which is to predict a sequence. And the idea here is to just, so it's actually a bit a continuation of what we have seen here, right? So here you got two words. You had to tell me, is this a real or fake instance of two words appearing in a real text, or is it just a random pair of words? So the next small anyway extension you could do is to take a sequence of words, word 1, 2, 3, sequence of words, and then you ask, what is the next one? So how does it continue to giving you a text which is not finished yet? Can you complete the text? Do you know which word would come next as this word WM+1? And that's another kind of learning opportunity. That's something you could train a system from, right? So here it was just a real fake, but the idea here is that we could also train a system from, maybe we can train an ML model which takes those so far and then predicts the next word. So the task of doing this is called language modeling. So here you have an ML black box, so I really don't care if this a neural network or anything. But the point is, it takes the word so far as the input and it learns to predict the next word. And there's like, this is a bit a harder task than the one before, which is just yes, no. So because here there are like 20,000 possibilities when your vocabulary size is 20,000. So, and okay, this is a very nice learning task, and that's actually how the most modern NLP models are trained, usually they're trained exactly on this task. So, or a slight variation of the task that you actually try to predict a word in the middle from the others. And here I'm trying to predict the last word from the previous one, but of course it's a very minor variation. So for example, BERT tries to predict some word, random word in the middle from the other surrounding ones. So again, it's very important to design these tasks to have a task to learn from. And that's one aspect. And the other aspect is that once you have it, this is also cool for another reason, because now you can actually use it to generate text. So now if you have trained this ML, it can generate any text you want. So you give it a few starting words and just let it continue word by word. You generate one more word, then you give it this thing again and tell it to again complete one more word. And that's language models. And that's you probably heard of this thing like GPT-3, which is one of the recent very big language models, which I would actually really encourage you to try out. The 3 is not really public, but there's actually open source ones which are like similar size, similar performance. And then the GPT-2, which is maybe a year before, is also public. You can download these models, and they give you the next word, and it's really a lot of fun because it can continue about anything. It can take a conversation. Two people are talking to each other, and then it can continue the conversation, which means if you can do that, then you can also act in the conversation, right? You can play like a chatbot, for example. You actually get a very reasonable chatbot from just this super naive training task, right? It's quite extreme, at least to me, like how simple this task is, how naive, and how we don't use any hard-coded knowledge about language, right? We don't do anything smart, right? We just train a very naive neural network on this simple task. But if you do it, it can do pretty amazing answers and continuations of text. These models are also the best models we have in the world to summarize text. It's almost like human quality on many machine learning or NLP tasks. Usually you can actually, to tell you what, it's a bit strange, right? Because in reality, nobody really cares about this task. We just care about this task for training. In reality, you wanted to do a particular other thing. You wanted to maybe summarize text or so. And it's not clear how to tell the model to do that. So what you actually do is you would just give it the original text you have, and then a little bit at the end, you will say, please summarize this. So you will say this in words, and then it will continue for you, and it will answer something like, here is a summary, and it will do the summary. So it's I find it quite fascinating how mathematically it's such a trivial task, but then what the thing learns when you train it again by naive stochastic gradient descent is actually can be quite smart. Yeah. So this is kind of a typical brute force, not so much smartness has gone into the model design, but then because it has been trained on so much data, has been trained unsupervised through the vast amount of data, it can do quite smart things. So yeah, what else can be done with these models? So maybe you've seen some cases. So it even works for code, right? You can give it code. You can in GitHub there is a model, same thing again, to continue code, right? If you write code, this can give you excellent suggestions and smart complete to continue your code. You actually write only the comment of what you want to have in a procedure, and then it will basically write the code which does what you wanted to have, which you first wrote as a comment or so. So this can also work quite nicely, but takes a lot of compute resource to train it. For example, I think this one only in electricity already costs like 4 million francs just in burned electricity. So it's not so CO2 efficient also, depending where the electricity is from. And Also, a lot of parameters are required. So then you would use larger neural networks. So for example, this one has 11 billion parameters, which is yeah, many gigabytes, just only to store these weights. And then everything it memorizes is of course numerically encoded in these weights, right? There's nothing else, right? It doesn't memorize, it cannot memorize the whole text because the text is like everything written on the internet ever. So, but he has kind of encoded this or compressed it into this numerical representation, which is just the weights of your neural network. And yeah, I guess the architecture of the network is not so important. So, okay, once you have such a model, then you can generate text, which is cool. And the other thing is you can also get features from it. So yeah, one is text generation. We talked about it, and two is the thing we actually mentioned first. So you can also get features from that. And yeah, how would you do that? Any ideas? So, I mean, you would just give it the text, and then you would look at the activations in the last layer, something like this. So this would be the kind of features you get from such a trained network. If you want to use it as text features, you can also do that. So yeah, it's kind of both representation learning because that's the features and also generation at the same time. Yeah, very similar to for example GANs, where we have also both. You can also generate and as well use the activations as features. So yeah, that's language models, and so then other ones, BERT or so is also an example of that, where the only change is you predict a few words in the middle and not at the end. But other than that, it's completely the same idea. Okay, that was it for language models. Another thing, this is a bit older, what you could also do is, we talked a lot about words, right? But then here was kind of cool that we can get a whole sentence, and the whole sentence then gets features by, yeah, using the activations after the network has seen all the words so far. Another way you could do this to get features for a whole sentence and not a single word is to use, for example, a CNN convolutional net. So what you would usually do is, for example, you fill word vectors as the rows here. So here's a sentence. For every word, you fill the row vector with the word vector. And then maybe you have your convolutional filter, which here is a filter which goes over 3 words and then just applies this linear filter on those words, gets a number. So that's what a convolution net would do, right? It's the same as what we had for images. So convolution here is, I don't know, 50 times 3, and that's a filter, and then you can have this anywhere on your text. So here is another one. You just slide it over the whole text, and then again you get these numbers, and then maybe here you have a pooling, because the text has variable length. It has, some texts are long, some are short. Well, you would like to get a representation which is fixed length, no matter if you feed short and long text. So maybe here you have you just take things like max pooling or something, which we already know from images as well, or you could also use average. So now we have a fixed length representation, actually just one number. But of course we can do this again with different filters. Then we get another feature and so on. So now this was a different way to learn a fixed length representation. So even when the text was variable length, right? So So this is just a neural architecture. This doesn't tell you how it's trained. So it's not so interesting, I would say. And also these were mostly trained just supervised. So here is a so it's just supervised training. Which is a bit less interesting because we have much less data which has this, right, which has labels. So for example, in the project, if you want to do this, there's data on smileys. So some texts have a, actually that's kind of an interesting idea, because some text comes with a positive smiley, some text comes with a negative smiley. It's already there. Can you use that as a training signal? And that's also an option. And the data set we give you, if you want to use this as a project, are texts which had smileys, positive ones and negative ones. This you could also use as a training signal to train a network. And one kind of natural network to train is a convolutional net, if you want. Although nowadays people have rather moved on to more like transformer-based architecture. So which can behave similarly. And again, the takeaway kind of is that it doesn't matter so much what the architecture is. What really matters is what it's trained on. So there is the interesting things you can do, and also to improve it for your use case, for example, in the project also. Okay, and there's not much left. So I want to finish with fast text, which is another actually really nice thing, which can be both supervised and unsupervised. And why we put it here is because it's kind of a nice way to both go beyond words. So this can do sentences. And it's also nice because it's super easy to train, and it really uses the exact same tools as we had. So it's actually also kind of a matrix factorization, but it's going beyond just word vectors. So it's allowing you to embed also sentences, to get features for sentences or maybe documents, which is important, right? So of course you can just take if you want to get features for your sentences, the naive thing to do is just to get the word vectors and then maybe average those. That works actually pretty well, right? It's a word is the sum of all the sentence is the sum of all the words which are present in it. That works okay. But there is something which is a bit better, and I will explain it here for sentence classification. So this is actually going to be for supervised. Supervised sentence classification or document classification. I don't distinguish between sentences and documents. It doesn't really matter. Or can be paragraphs. Though it's kind of interesting if you ask, of course, we represent a word as a point. So now we have a word representation. Then we ask, can we represent a sentence as a point? So all good, can we have a paragraph or an entire document as a point? But then when you ask about, can you represent an entire book as one point, then it gets a bit tricky. So then it's a bit unclear if that's still meaningful, or can the whole Wikipedia be one point? I don't think that would make sense. So the role of length here is kind of nice because, or kind of interesting. So because it's really a bit unclear what is the granularity that we want to represent, right? So are we interested in doing something with words or with entire books or so on? And but it depends on the use case, right? So but I think in real use cases often it makes sense that you ask to do something with like a sentence or so. Maybe that's even more practically relevant than just words alone. So okay, so here is, assume we're given a bunch of sentences and we have labels for them. So maybe they're labeled into being emotion positive or emotion negative, or or whatever as relevant for your business or not relevant. So you have manual labels. These labels are the labels Y. So plus minus 1 is a label I have for every sentence N. Then, and again, I'm trying to learn a matrix factorization, and I also have the text of the sentence, and actually here I will use the bag of words. So so bag of words. So that's xn is my sentence representation, and that's just going to be a 1 at the words which appear in my sentence, and 0 otherwise. Present words. So okay, so this sounds a bit naive, right? Because we said bag of words is kind of the naive way. It's not going to lead to such good representations. But let's see, because maybe it can be combined with some embedding idea. So, and again, here it's very clear why it's bag of words, so because it's not just one word, right? Here my sentence has 3 words. So there's ones here for those words which appear in my sentence. Okay, that's it. So then how can I convert this representation, the naive one, into a really useful one of the sentence? And that's here. So I just multiply with an embedding matrix of the words. So this is the sentence representation. So what is this Z matrix? That's the question now. So the Z matrix has a column for every word. So, and then it's quite big. It has because there are lots of words. So I just, again, the vocabulary size, maybe 20,000 or 100,000. So, okay, I just decided I want to learn such a Z matrix. Why not? That's a word embedding matrix, right? Because it's convenient for every word there will be an entry here in this Z matrix. Yeah, and again, how many dimensions do I want to have? How many features does each word vector have? That's K. So you choose it to something. Okay, that's the Z matrix. So now the idea is that if you multiply Z with the bag of word, you just get the average of these 3 vectors. So, and that average is your sentence representation. And yes, that's it. So that's how you can get from bag of words to an embedding of a sentence. Here our sentence had 3 words. So now we have a sentence vector, and now we still need a classifier on that resulting sentence features, and that is the W. W is a 1 by K matrix, which sounds a bit stupid. So it's actually a vector. So that so W is really just a K vector. So it takes the sentence to its right. You left multiply the sentence with W, and that means you have now a number when you multiply W with the sentence representation. So you have a number, and then with the label, what this says is just, it says that, yeah, the positive sentence should have a positive score, and the other class of sentences should have a negative score. So F here is really a standard linear classifier loss function, and the label is already here, right? So it's just gonna, well, you could even use the identity here. So you just want this to be positive. So, but you can also think it as logistic regression. You just have a data point here, which is the whole sentence, times a linear classifier. So W is a vector multiplied with this nice matrix here. Okay, so now we have a sentence supervised classifier. And why is this good? So what's interesting here is that it again is a matrix factorization. It looks, we are very familiar with this kind of thing, right? Where there's two types of parameters, the W, which is quite a small number of parameters, and the Z, which is a big set of parameters. Anyway, we learned these two. We learned them by again, stochastic gradient descent, do an update on W, do an update on Z. It's really efficient here because you can convince yourself that again, you can train this streaming through the text, well, streaming through the data set. So you have a bunch of sentences with labels. For every sentence, only the word vectors which are present in the sentence, only those will be active here. Only those will be added up. So only those will contribute to the loss. So then only those will be in the gradient. So only these guys will have an update. So the update is very cheap again. So for every word in your sentence you spend again the cost K to compute the inner product of the word with the classifier. And that's it. So an extremely efficient classifier, which can be quickly updated with HTTP. And why it's also interesting is because it's still going a bit beyond linear, right? So because if you just learn W, then it's boring. Then it's what we had before: static data, learn classifier. But this is more cool because it's non-linear, because two things are learned. Z is learned and W is learned such that they play well together. So that's why it's kind of a two-layer thing. It's getting a non-linearity because W times Z is non-linear, and we learn both those to do the job. So it's not only finding good W, right? It's finding embedding Z and W, which do work nice together. So that's like it's two layers, and it seems this is already a big step. So you don't need neural networks of depth 100 or so for some simple tasks. So sometimes it's enough to have rather simple models and simple non-linearities here, which can also be very efficient. So this is nice if you need a supervised learning for sentences, can be quite fast. There is also a kind of an unsupervised version of this, but we're not going to discuss it. When you use a similar loss function as here, you could also use it to predict if the next word is real or fake. So, but we're not going to do that. So here, just think of it, this is a supervised method, but it's a nonlinear one, which makes it a bit more powerful than just linear classifiers. And still comes at the price, which is almost as cheap as any method we have seen. Yes?
Can I ask a quick question about this?
Sure.
In the end, when we get a model, will that model be able to embed a whole sentence?
So the model we get from here is Z and W, but maybe you're most interested in Z to get sentence representations. And your question is if that Z I get here is also going to be able to represent any new sentence. So that was your question. And yes, actually, pretty much, yeah. So because, yeah, if you have a kind of large enough training set, then these embeddings here will be very reasonable for all the words. They will already be meaningful. And then any sentence in the future will be consisting of the same words. So yes, and what this does, it kind of trains the word vectors to be added up in a meaningful way, or it trains the word vectors to be such that they can be either added up over the sentence and still have a meaning which makes sense. So it's a bit smarter than to just take fixed word vectors from word to vec and add them up afterwards. But here they are trained to be added up. So because already doing training, this happens. So this gives a bit better embeddings than if you just take static embeddings and add them over your sentence. And I would say that's it for today. And also there's a few links in the end. And next week we take some time off so you can work on a project. And it was a pleasure having you guys and girls here on Zoom and on the real room and anything. And have a nice Christmas break. and see you sometime soon. Thanks.